Hi, we're going to take a look at the Knobster DIY project. I've been using Air Manager in Microsoft Flight Sim 2020, and it works great. I'd really like to use the Knobster, but I have a hard time justifying the $100 plus cost of a knob and a USB cable. I realize what work has gone into making it happen, and I appreciate that certainly, but I just couldn't justify that cost when there's a DIY solution available. Air Manager mentions on their wiki a DIY project using an Arduino and a knob, but there wasn't a lot of information available to do the wiring and how to set it up, so hopefully this will help someone else in the efforts to figure that out. So they mention this product, this encoder, which is available from PropWash Simulation. It comes with a dual encoder with a push button, a center push button. Forgot the knobs here. And it comes with the little board, a small PCB, and the header pins here. But it's all separate, and I had to solder them all together. So just requires a little bit of soldering. The encoder fits nicely into the board. It will fit in either way. So I guess depending on how potentially you're going to lay this out physically, mounted on a panel, you might want to do it one way or the other. I don't think it matters, except for ultimately which of the pins. There's a small AB and a big AB pin. Which of those end up getting wired to which of the encoders, the inner or the outer. That's really the only key difference. It actually doesn't matter which way this is soldered onto the board, whether you put the encoder on this side of the board or on this side of the board. The pins are wired from the front to the back, or from the one row here and one row here, matching up to one set of pins on either side. The difference really is whether B or A is a contact going in one direction or the other. So that could affect potentially needing to switch these two pins based on the direction. So once you use the sketch in Air Manager, it's possible that you could be going the wrong direction, and it's just a matter of swapping the two A and B to make sure that the direction's correct. But one encoder is always going to go to the small AB, and the other is going to go to the large AB. So these pins are the encoder pins, and then the two on the end are the push button pins. So then I also got the Arduino Nano for the interface of the computer, obviously. And then from SparkFun, I got a set of connector wires to, I don't know the breadboard, but I really didn't have the wiring to mess with things. So there's a dual female to female set of wires. Then I also got a kit of the male pins to female connectors, and then also the male to male pin to pin for going through the breadboard. Those are a few dollars each. The dual encoder board was, I think, about $12 for two of them. Comes with two. And then from SparkFun as well, I got a 500 count resistor kit of various resistance levels for, again, just a few dollars. 100 or 20, I think, each of different resistance levels. I did have some old resistors, but I wanted to make sure I had some newer ones in the different resistance levels. Then for this project, I also used some old red LEDs, fairly ancient LEDs. I dug up some old resistors too before I had the other ones. And then an old breadboard from years and years ago, back when Archer was actually a thing, if anyone remembers the old Radio Shack days. So I wrote a basic sketch for the Arduino that just takes the different inputs of the encoder and makes the lights turn on. I looked online, saw a couple videos trying to understand how the encoder works. I did see mention that each click of the encoder results in two pulses. I didn't entirely understand what that meant. I wanted to learn more. I did hook up the encoder to a multimeter for continuity check to see which pins connected to which as each thing happened, and I saw connectivity between the common lines and the contact lines for the different encoders at the same time. I wasn't really sure why, based on what I'd been reading. That didn't make sense to me. So there I set up this little program to check. So the program's running. There's for each encoder there's two contacts, the inner for the inner and the outer, and then the push button is a fifth contact. So when you turn the encoder, you can see two lights come on. Turn again, goes off. Same the other direction. That's the outer encoder, then there's the inner encoder. And then the push button, the fifth LED. What's happening is that for one click of the detent of the encoder rotator, there's actually two contacts being made. If you turn it very slowly, you can see the LEDs. The first one turns on the left, and then you click it, and then the second one turns on. And then they turn off when you go to the next detent. Going backwards, up to the left, you'll see, turn it just a little bit, the right LED turns on. Again, the left LED comes on together. And then again, turn left one, click, and they both turn off. Same thing with the other encoder. Turn on and off in sequence, going left and going right, and then going left. And that's the secret to the encoder. Your programming can then track the state of each input to determine which direction, to the right or to the left. Whether they go on or off is really not relevant. The programming just needs to track the state change of each input in sequence. And as long as the program can run as fast as the inputs can fire, you can track the state or the direction of the inputs. So a few more points about the wiring here. The inputs on the digital input pins do require a resistor to either pull them up or pull them down to null out the input levels, so you can actually tell the difference in the input state. The high state, so this line is coming from my the VCC plus 5 volts. That you can go directly to the pin, but you need to zero that out when you're not connected so that it knows whether the state is actually high or low. There's plenty of resources available for understanding how those work, and those I did find very useful. So the inputs from the encoder are going into the breadboard for the digital input pins, and then also from each of those inputs we're going over here to a pull down resistor in this case. Zoom in a little bit, let me see this better. So each of those inputs is going through a pull down resistor, which then goes to the ground bus that all these other things are connected to. When you make contact in the switch, so each of the contacts then shorts between the plus 5 directly to the pin to establish the high level input, and that gives you your actual positive high input into the program. When those are not connected, it's going through the pull down resistor to ground to bias it to low, down to 0 to ground. Then the resistors are connected with some resistors, because that's the way the LEDs are connected through resistors, because that's the way LEDs like to work. These are old resistors, so they need fairly low resistance because they need a little more power. Old LEDs rather, so they need older resistors, so they need a bit more power. And that's just standard LED hookup. So then within the program, I'm just tracking the state of the inputs and tracking, the up and down state, so that as I rotate the encoder, we can see the outer rotor is just tracking an increase. Turn it left, a decrease. The inner rotor, same thing. And then the push button is just, is it pressed or is it released? Just tracking the state of that. Fairly simple program. just to demonstrate the encoder behavior. I haven't yet loaded the Air Manager provided sketch to actually turn it into a Knobster. That's the next step, but this is just a look at how the rotor works and some basics of the wiring for the encoder itself. Hope that helps.